Hello everyone, welcome back. So in this video we are going to learn about basics of transmission lines. So if you are new to my channel, please consider subscribing. So in this video we are going to learn about the basics of transmission lines. Okay, so transmission lines. So generally a transmitter, so what is the job of a transmitter is it converts the source signal, that is electrical signal or source signal, into EM wave. So it converts this source signal into EM wave. So this channel, this EM wave is now passed through the channel. So this EM wave is passed through the channel, and this EM wave will travel through the channel and travels from transmitter to the receiver. So at the receiver end, this EM wave is again converted into the original source signal. Okay, so it is again converted back into its original source signal. So this is what we are going to do in this is what it is happening in electromagnetic wave transmissions. Okay, so if the distance between the transmitter and this receiver, so if the distance between them is greater than 10 kilometers, so we use unguided propagation. We'll use unguided propagation, or it is also called as wireless propagation. Okay, so wireless propagation. So if the distance between transmitter and receiver is less than 10 kilometers, then we'll use guided propagation. So we'll use a guided propagation. So in guided propagation, again at low frequencies, so at low frequencies we will use transmission lines, and at high frequencies we'll use waveguides. Okay, so this is how we are going to use transmission lines and waveguides in guided propagation. So both are used in guided propagations, but at low frequencies we'll use transmission lines, and high frequencies we'll use waveguides. Okay, so in unguided propagation we know we'll use antennas. So in the unguided propagation we'll use antennas. So this is why we require to learn about both transmission lines and waveguides in order to have an idea of guided propagation. Okay, so transmission line is basically consisting of two conductors. Transmission line basically consists of two conductors which are used to carry electromagnetic wave from transmitter to the receiver. Okay, so it consists of two conductors. This is important. So it consists of two conductors which is used to carry the EM wave from transmitter to the receiver. Okay, so next is equivalent circuit of transmission line. So the equivalent circuit of transmission line. So equivalent circuit is like this. So this is the equivalent circuit LR. So RL G C. So this is the equivalent circuit of a transmission line. So these R, L, G, C, these are called as primary constants. So these are called as primary constants of transmission line. So this the R is called as series resistance measured in ohm per meter, and it is due to non-ideality of conductor. So it is due to non-ideality of the conductor. And second, L is called as series inductance. Series inductance measured in Henry per meter, and it is due to magnetic field. It is due to magnetic field when current is flowing through the transmission line. When current is flowing through transmission line. Okay, so third, G. This G is called as shunt conductance. It is called as shunt conductance measured in mho per meter or Siemens per meter. So, and it is due to the non-ideality of dielectric medium. It is due to non-ideality of the dielectric medium present between two conductors. Okay, similarly the fourth one, C, which is capacitance, and it is shunt capacitance because it is in parallel and these two are in series, so they are called as series resistance and series inductance, and since they are in parallel, so this is called as shunt conductance and this is called as shunt capacitance. Shunt capacitance measured in farad per meter, and it is due to electric field. Since series inductance is due to magnetic field and now it is due to electric field. It is due to electric field when a voltage is applied. When voltage is applied to transmission line. Okay, so these are the four primary constants of transmission line. Okay, so since the R and L are in series, so series impedance Z is given by R plus j omega L ohms per meter, and shunt admittance is given by G plus j omega C mho per meter. Okay, so this is series impedance and this is shunt admittance. Next is secondary constants of transmission lines. So there are two secondary constants for transmission lines. One is characteristic impedance, which is represented by Z0, and Z0 is given by root of Z by Y, that is series impedance, the ratio of square root of series impedance to shunt admittance. It is given by R plus j omega L by G plus j omega C ohms. So this is called as characteristic impedance, which is represented by Z0. Okay, the second secondary constant is the propagation constant. Which is represented by gamma, is given by root of Zy. This implies root of R plus j omega L into G plus j omega C per meter. So its units are per meter for propagation constant. So these two represents the secondary constants of transmission lines, and R, L, G, C represents the primary constants of transmission lines. Primary constants of transmission lines. Okay. So in when the transmission line is propagating in low frequency region, so when the transmission line is propagating in low frequency region, so what is low frequency region? So when the frequency is low, then omega L is very much less than R. So in the series impedance formula, so omega, since it is at low frequency, so omega L is less than R, and omega C is very much less than G. So under this condition, so what is the value of gamma? So Z0 first. So Z0 is equal to, so since omega L can be neglected, Z0 is given by root of R by G, and similarly gamma is equal to root of Rg. So root of Rg. So in low frequency region, Z0 is purely resistive. So Z0 is purely resistive, and gamma is a real term. Gamma is real. At which region? In low frequency region. When the transmission line is operating in high frequency region, so at very high frequency region, then what is the condition? Omega L is very much greater than R, and omega C is very much greater than G. So under this condition, Z0 is equal to root of L by C, and gamma is equal to J omega root LC per meter. So under this condition, Z0 is again purely resistive. Z0 is purely resistive, but gamma is imaginary. This is important. So in high frequency region, gamma is purely imaginary, and in low frequency region, gamma is real. So when transmission line always operates under low frequency region, so when it operates under high frequency region, there will be losses. So losses occurs in transmission line when it is operating in high frequency region. Okay. So the next concept is propagation constant. Propagation constant, which we already have discussed, but we have to write the formula for attenuation constant and phase shift constant. So generally, propagation constant gamma is the combination of alpha plus j beta, and its units are meter, where alpha is called as attenuation constant. It is called as attenuation constant, measured in Nepper per meter, and beta is called as phase shift constant. So it is called as phase shift constant. It is measured in radians per meter. Okay, so we know that gamma is equal to root of zy, which is given by root of r plus j omega L into G plus j omega C. So squaring on both sides, we get gamma square, which is equal to alpha plus j beta whole square is equal to r plus j omega L into G plus j omega C. So this becomes now alpha square minus beta square plus j into 2 alpha beta is equal to Rg plus j omega L R plus j omega C R plus j omega L G plus minus omega square LC. So if you take equating real parts and equating imaginary parts and solving for alpha and beta, we'll get the equations for alpha and beta. So I'm writing directly here the equations of alpha and beta because we require these equations. So alpha is given by under root of 1 by 2 into Rg minus omega square Lc plus root of R square plus omega square L square into G square plus omega square C square, G square plus omega square C square Nepper per meter. So this is the formula for alpha. Similarly, we'll get the value of beta as under root of 1 by 2 into omega square Lc minus Rg plus root of R square plus omega square L square into G square plus omega square C square. Okay, so units are radians per meter. So this is how we'll get the values of alpha and beta, where alpha is called as attenuation constant and beta is called as phase shift constant, and the combination of alpha and beta is called as gamma, which is an imaginary term. Okay, so this is about propagation constant.